Today we will be finding the derivative of an inverse function at a specified point. Before we begin, we're going to talk about notation for the inverse of a function, because it can often be confused with the notation for 1 over a value. So this 3 to the negative 1 is equal to 1 over 3 to the positive 1. So we see when we have a negative 1 as an exponent on a number, it makes it 1 over that number to the positive 1. 7 to the negative 1 is 1 over 7. 4/3 to the negative 1 would be 3 over 4. X to the negative 1 is 1 over x. That is true. So we know that any number or variable to a negative 1 power is 1 over that variable or number. Does that mean that sine to the negative 1 power is 1 over sine x? And I've said that wrong, actually. It looks like sine to the negative 1 power. It's not actually sine to the negative 1 power, because sine is a function. Sine is not a number or a variable that represents a number. Sine is a function. So no, this does not mean 1 over sine. Okay? Now, sine of x to the negative 1 power is 1 over sine of x. But this notation, somebody a long time ago decided to make that notation the notation for the inverse of sine. Okay? So when you see this negative 1 on a function, any function, it does not mean 1 over, it means the inverse of that function. I don't know why they use that notation for inverse, but they do. So we have to live with it. So there you go. So f to the this notation is read f inverse of x. It has nothing to do with 1 over f of x. G inverse is the inverse of g. Okay? This is calculus. We're going to be finding the derivative of a function's inverse. Specifically, we're going to be finding the derivative of a function's inverse at a certain value of x, at a certain point on the function. Okay? So first of all, I would ask you, how would you write the derivative of the inverse of f? If the inverse of f is written like this, how would you write the derivative of the inverse of f? So one way to do it would be, there's f inverse prime of x. And that is officially the way that we denote the derivative of f inverse of x. Okay? So, a quick review of inverse functions. If f and g are inverses of each other, it means that each of these three things are true. If AB is on the curve of f, then BA must be on the curve of g. That means if f of A is B, then g of B must be A. We call these corresponding points. Okay? So I'll be referring to that word corresponding points. All right, the two curves are symmetric to each other with respect to the line y is equal to x. A great example of this, because we have just finished working, well, we're more familiar with these, is the graph of e to the x. This is y is equal to e to the x, and this is y is equal to ln x. So these two functions are inverses of each other, and it is clear that they are symmetric to each other with respect to the line y is equal to x. And then the last thing about inverse functions is that their compositions each yield x back. So f of g of x is x, and g of f of x is x. It makes sense because if they're inverses of each other, they undo each other. So f undoes g and gets back to whatever's in there. And G undoes F and gets back to whatever's inside there. So F of G of, say, 2 would yield 2. Okay? So the composition of F of G of 2 would be back to 2. All right. Now let's examine the derivative of a function's inverse. We are given that G and F are inverses of each other. Let's find G prime of X. Okay? Well, if F and G are inverses of each other, then we know that F of G of X must be X. So F of G of X must be X. It must be if they're inverses of each other, which we are told that they are. So we are going to come in, since we want G prime, I'm going to come in and take the derivative of each side with respect to X. And we know how to take the derivative of an inverse function. It's using the chain rule. Take the derivative of the outside, F, keep your inside the same, and then multiply by the derivative of your inside, G prime of X. And the derivative with respect to X of X is just 1. And now solving for G prime of X, we're just going to divide both sides by F prime of G of X, and we get G prime of X is 1 over F prime of G of X. Okay? So we've learned something very valuable. Inverse functions have reciprocal derivatives. They are reciprocals of each other. Okay? They are reciprocals of each other at their corresponding points. At their corresponding points. So let's write that in this box on the next page. If F and G are inverses of each other, then G prime of X must be 1 over F prime at its X value. Now its X value would be G of X. I like to think of this, here's what I like to think of this as. It makes it a little bit easier for kids to understand. G prime is equal to 1 over F prime at corresponding points. That's your go-to right there. So if AB is a point on F, then BA is a point on G. So G prime at its X value, there's G's X value, is 1 over F prime at its X value, A. So AB is the point on F. All right? So G and F are, the derivative of G is the reciprocal of the derivative of F at their corresponding points. Let's take a look at how you might be asked questions involving inverse functions derivatives. Here's one way I've seen on multiple choice questions on the AP exam. If F of 2 is 5 and F prime of 2 is 1/3, then what is the derivative of F inverse at 5? Well, as soon as I see something involving inverse functions, I think to myself, okay, the derivative of F inverse is 1 over the derivative of F at their corresponding points. At their corresponding points. So I am looking for the derivative of F inverse at its X value of 5, and that will be 1 over F prime at its X value when its Y is 5. So for the sake of your notes, this is F's X value when Y is 5. And when Y is 5, they gave us they gave us that x would be 2. And now we have 1 over f prime of 2, and they gave us f prime of 2 as well. F prime of 2 is 1/3. 1 over 1/3 is 3. So the derivative of f inverse at 5 is 3. Okay? Let's take a look at another one. Let's say that they give us that f of x is this function, and we want to find the derivative of f inverse at 8. Well, I know that the derivative of f inverse at 8 is 1 over the derivative of f at its x value. At its x value. Very unlikely it's going to be 8, unless it just happened to be the 0.88. All right? So we know that y is 8, and we want to know what x is equal to there. Well, if I know f, and I know that f is equal to 8, I should be able to find x. So I'm going to take my f of x, 3x cubed plus 5, and set it equal to 8 to find x, to find the x coordinate when y is 8. So if I subtract 5 from each side and divide each side by 3, I get x cubed is 1, and that means that x would be 1. So this x value is 1. And now all I have to do is find f prime of 1. Well, they gave me f of x. I know how to find f prime of 1. So f prime is 9x squared. F prime of 1 is 9. So f prime of 1 is 9. So we get 1/9 for the derivative of f inverse at 8. 1/9. Okay? How else could they ask us questions? Well, they could ask us questions in a table format. Alrighty. Let h be a differential function, and selected values of h and its derivative h prime are given in the table on the right. Part A, find the derivative of h inverse of 5. As soon as I see an inverse, I think to myself, the derivative of h inverse is 1 over the derivative of plain old h at their corresponding points. That's my thought. I don't write it down, but that's what I'm thinking. So, h inverse derivative at 5 is 1 over h prime at its x value that makes y 5. Its x value. This x value makes h's y value 5. So what x value makes y 5 on the graph of h? So I go to h here in the table. I want the y value to be 5. Well, the y value is 5 right here. That's when the y value is 5. The x value that makes h 5 is 10. Now all I need is h prime of 10, and they gave me that in the table. So this is negative 1/4, and 1 over negative 1/4 is the flip of negative 1/4. That's negative 4. So that is negative 4. And then part B, let's write the equation of the tangent line to the graph of h inverse at the point when x is 7. Well, I know if I'm writing the equation of a line, I need a point and I need a slope. the point is going to be on H inverse. It has to be because that's where our line is tangent to. So the x-coordinate of H inverse is 7. The x-coordinate of H inverse is 7. How are we going to find the y-coordinate? Now this point is on H inverse, not on H. It's on H inverse. So how are we going to get the y-coordinate for H inverse? Well, we're going to have to examine the graph of H. So I'm going to go off to the side. The point on H would have y-coordinate 7. Which point on H has y-coordinate 7? Well, if I go to the graph of H, I'm going to go to where y is 7. There's where y is 7. Its x-coordinate is 3. So H inverse's y-coordinate must be 3. Made that a little close. Let me scooch it down for the slope. The slope is the derivative of H inverse at its x value of 7. Well, I know that that's 1 over H prime at its x value, and now I know what its x value is. Its x value is 3. And so we get 1 over H prime of 3. We can go to our graph and get H prime of 3, negative 3 halves. And when you take the reciprocal of negative 3 halves, you get negative 2/3. So the equation of a line of the tangent line would be y minus the y-coordinate of H inverse is equal to the slope times x minus the x-coordinate on H inverse. And that is an equation of the line tangent to H inverse when x is 7. Okay, take a look at a couple more examples here. Number 4. If, focus this little hair more, if G is the inverse of F, if G is the inverse of F, and F is sine of 3x with x between 0 and pi over 4, then G prime at 1/2 is what? As soon as I see that G and F are inverses, I know I'm using that condition that inverse functions have derivatives that are reciprocals of each other at their corresponding points. I am looking for G prime of 1/2. So I'm going to write G prime of 1/2 is 1 over F prime at its x value that makes y 1/2. We need to find that x value that makes y 1/2. F 1/2. F's y 1/2. So we're going to find x that makes F be 1/2. So I take my f of x, set it equal to 1/2, and solve for x. Now we're back in pre-calc and we are solving this little trig equation. I need sine of some angle to be 1/2. Sine of some angle to be 1/2. Well, what angle makes sine 1/2? I know that sine is 1/2 at pi over 6 and at 5 pi over 6, right? That's where sine is positive 1/2. So the angle, the 3x, makes sine 1/2 at pi over 6, at 5 pi over 6, and then we could keep on going around and around the unit circle to get more and more angles that make sine 1/2. But this is why they gave me this condition. This is going to allow G inverse to be a function, because we're only going to get one x value that makes sine of 3x equal to 1/2. If I multiply both sides by 1/3, I get that x is pi over 18, 5 pi over 18, etc. But 5 pi over 18 is outside of our interval, so we exclude it and we exclude anything after that. So the only value of x that makes this true is pi over 18. So now we need to find f prime at pi over 18. Well, I know what f of x is. F of x is sine of 3x. And I know how to take the derivative of that and plug in a number. So f prime is the derivative of sine is cosine. Keep your argument. Now a little chain rule, multiply by the derivative of 3x. So f prime is 3 cosine of 3x. So f prime at pi over 18 will be 3 cosine of pi over 6, which is 3 times cosine of pi over 6 is square root of 3 over 2. So this is 3 square root of 3 over 2. Okay? So back up to my little expression here, my equation. F prime at pi over 18 is 3 square root of 3 over 2. So g prime at 1/2 is the reciprocal of that, so 2 over 3 square root of 3. D. All right. Nobody likes that one when I do it in class. All right. One more example here. Let f and g, this is more of an FRQ style. The functions f and g are differentiable for all real numbers. G is strictly increasing. The table gives values of their functions and their first derivatives at selected values of x. Part A, find the inverse, the derivative of f inverse at 6. The derivative of f inverse at 6. Well, the derivative of f inverse at 6 is 1 over the derivative of f at its x value that makes y 6. I'm going to write that down. This x value makes y, or f, be 6. So I go to my table. I need the x value that makes f 6. Well, right here f is 6. The x coordinate is 1. 1 over f prime of 1. F prime of 1 is 4. So the derivative of f inverse at 6 is 1 over 4, 1/4. Part B, write the equation of the line tangent to the graph of f inverse when x is 9. Well, I need a point and a slope if I'm going to write the equation of a line. So point, slope. The point is on f inverse. The point is on f inverse, and its x coordinate is 9. How do we get the y coordinate? We're going to use f, because up here in the table they don't give us any information explicitly about f inverse. They only give it about f and g. So I want the y coordinate on f inverse, and the y coordinate on f inverse is the x coordinate on f when f is 9. So on f, the y coordinate will be 9, and I want the x coordinate. Well, the x coordinate that makes f 9 is 2. The point 2,9 is on f. So the point 9,2 is on f inverse. That's the point we will use for our equation of the line. Slope. The slope will be the derivative of f inverse at its x-coordinate of 9. At its x-coordinate of 9. That is 1 over f prime at its x-coordinate, which we now know to be 2. F prime of 2 is 2. So the slope is 1/2. Therefore, the equation of the tangent line would be y minus f inverse's y-coordinate is equal to 1/2, the slope, times x minus the x-coordinate of f inverse. Okay? The last part of this says use the equation of the line tangent to the graph of f inverse when x is 9, found in part B, to approximate the value of f inverse at 9.5. Well, this equation that we found in part B represents an approximation for f inverse of x. So f inverse of x would be, if we add 2 to an approximation for f inverse would be 2. We're moving the 2 over. That's an approximation for f inverse. So f inverse of 9.5 would be approximately 2 plus 1/2 times 9.5 minus 9. And we could simplify that if we needed to, but this is an FRQ, so I'm going to stop there. So that is derivatives of inverse functions at specific points. It can be kind of confusing, but this is how we do it.